Big Bang cosmology. That is a model in physics which you use over here to say how we evolved to the present time. It posits that about 13.8 billion years ago, there was a very fast inflation that happened. That inflation is called a Big Bang. And somewhere around 380,000 years later, we had this cosmic microwave background. And around 200 million years after that initial inflation, that is when light, stars, galaxies formed. And now 13.8 billion years ago, we are here today with so many stars we see in the sky, so many galaxies that we see. This is what we say, and currently science posits that this happened in 13.8 billion years ago. And the model for this one is through the Big Bang cosmology. How did they infer this? Through the data. What kind of data? All the galaxies seem to be fleeing away from each other. So there's an expansion happening. So they work backwards and say there must have been a time when everything was compressed into a small point or so on. That's how this kind of model came about. Then today we got something called the fine-tuned universe. So here, as physicists are saying, there are some elementary standard charges, mathematical constants like elementary charge, constant of gravitation, Planck constant, speed of light in vacuum, electric permittivity in vacuum, magnetic permeability in vacuum, electron mass. These numbers are so small that you can see 10 to the power of minus 19, minus 11, minus 34. And they say even if it was off by a small value, instead of 10 to the power of minus 34 to 10 to the power of minus 33 in Planck's constant, the evolution of our universe would have been different. So they say that we have got a very finely tuned universe that owes its existence to these numbers the way they are. Once again, this is an outcome of astrophysics. How will time end? There are two theories over here. One theory says this expansion will go on forever and ever. It's an open universe model where eventually all galaxies will recede so far away from each other, we won't even see stars in the sky. Well, we won't be there anymore, but that's in trillions of years from now. That is one model of expansion happening forever. There is another competing model that talks about the big crunch. It says that as we go through a maximum expansion, some other forces of nature are going to come, dark energy, dark matter, and other such things will come into play. And we are now going to see in a closed universe a big crunch also happening, giving rise to another universe perhaps at a later point in time. But these are two very seriously discussed methods in astrophysics to try and talk about the fate of the universe using models of this kind. So in cosmology, we call this a big bounce model. In the big bounce cosmology, you have a prior universe. And this prior universe goes through an expansion. As it contracts, it goes through an expansion and starts a new inflation and a new universe of this form. So this is very intriguing for Hindus who also believe in a recurrent creation and destruction cycle. So it is very intriguing that even physics today is contemplating that there is a big bounce cosmology where we could have this kind of a recurrent creation and destruction of the universe in huge timelines. Then this is an intriguing paper that came about from Professor Roger Penrose, who is an astrophysicist in UK. So he brought about a theory that there is evidence for what he called Hawking points in the CMB, cosmic microwave background sky. So according to him, if you take a look at this picture on the left, it says that once you have this expansion event happening and galaxies taking root, after maximum expansion you have contraction, and this universe has got black holes in addition, right? These black holes will decide how the next universe is going to evolve. So in a sense, it's like Vasana, the Vedantic Vasana, where we say that our prior births, karma, decides what ruts we follow in the present life. We are drawn to certain habits in this lifetime because of the Vasana from the previous life. It's very intriguing that such a Vedantic concept can be applied to this also. The question to ask is, if the expansion event is uniform and symmetrical everywhere, why don't we see equal number of galaxies in the sky, equal number of stars? Anywhere we look, we must see symmetry. But we don't see symmetry. We see some places where there are more of these stars and galaxies, some places where there are less. And the reason for that, according to this theory, is because of some impact of the black holes of the prior universe controlling the evolution of the present universe.